All right. So now projectile motion. Now let's look at it one more time. So when I launch an object, look how the horizontal velocity, which is the green arrow that's pointing horizontally, remains unchanged. And your vertical velocity, okay, so now let's focus on the vertical velocity. If I start it, your vertical velocity starts with a huge number. And then it keeps, as the ball goes up, the vertical velocity keeps getting smaller and smaller because gravity is slowing you down in the vertical direction. Actually, one thing funny is the highest point. Now, this moment, at this very moment, your object is at the highest point, like right here. At this moment, let's see if I can actually move this. Okay, apparently, if you zoom in, you cannot move it. But at this moment right here, your object is at the highest point that it could ever get during this fight. However, at that moment, your vertical speed is also 0, which makes sense because remember when we did our free fall, right? At the highest point, we assume your speed is 0. When we did our free fall question, we say, oh, you have some initial speed going up, and then you get to the highest point, your speed is 0, and then you slowly come down again, and you get speed up again because of gravity, and at the end, your speed will be negative of what it was before. So what goes up must come down with the same speed, but at the maximum point, the speed is always 0. Now, so it's still true right now, except that we are only talking about the vertical speed. So if you only talk about the vertical speed, yes, the vertical speed will start with a huge number, for example, like this. So it will start with a big number, and then it will just get smaller and smaller as time goes by. And at the highest point, your vertical speed is completely gone. Yep. So at the highest point, right, your vertical speed will be completely gone. So let's look at that again in here. If I fire the object, look at the vertical speed getting smaller. Now the vertical speed is this green arrow in here. So the vertical speed keeps getting smaller and smaller, and then it keeps getting bigger and bigger again because gravity pulls you down, right? So by the time you hit the ground, the vertical speed is a huge value. Now, but notice the horizontal speed, one more time, is not changing. Look at that horizontal speed. The horizontal component of your speed remains constant throughout the entire fight because nothing is pushing the object to the right and nothing is pushing the object to the left. Then that means right now, right? That means right now we have two different conditions to consider. We have two directions, X direction, horizontal, and Y direction, vertical. It turns out that the vertical direction is going to be exactly like the free fall question that we did, which is you have some V initial. At the end, you have at the highest point, you have a speed of 0. And then when the object comes down, you'll get some negative speed. And then we have a horizontal part, which is just constant speed. So the horizontal portion of this motion is constant speed. Now, and the good thing is that they are actually independent to each other. Only things that are vertical can affect things that are vertical. So for example, your vertical height. Now, what is your vertical height? Your vertical height is usually what is called maximum height of your object, right? Your vertical height will only be affected by your initial vertical speed, like this value, and gravity, which is also vertical. It will only be affected by those two things. However, your horizontal range. Now, what is horizontal range? Horizontal range is when the total distance that your object travel horizontally, right? So for example, in this case, it will be the distance between the cannon and the landing site horizontally, like this distance, which is, I can move the target there, which is at this point 25 meters away from the cannon. So that horizontal distance will only be affected by the horizontal velocity, which is the constant value. Okay, so now with that in mind, let's go back to here. Okay, so this is a little diagram, from the note that is similar to what we saw on our simulation. So as you can see, at the beginning, you have a speed of like this, right? This purple one is your initial velocity, but we're gonna break it into X and Y components. So there is an X portion, which is the blue one, and then there's a Y portion, which is the orange one in here. Now, as you can see, the blue portion, which is the Vx, remains the same Vx throughout the entire fight. Look, it's the same number no matter when you measure your horizontal speed. That means a good thing, which is we don't have to worry about horizontal speed too much. It will be the same number from the beginning to the end. And that if we have that value, it will tell us how to calculate the horizontal distance that it traveled. Now, however, the vertical speed, which is the orange value, right, orange arrows in here, the vertical speed is changing. At the beginning, it's at some like initial point, initial speed, and then it keeps getting smaller and smaller because of gravity. At the highest point, that Vy is technically gone. So at the highest point, that Vy is 0 at the highest point. And then it starts to become negative again and growing on the other side. And if you catch the object at the same level that you release it, still, what we said before is true. What goes up must come down with the same speed, just opposite to each other. So what goes up is your V initial Y. What comes down is your V initial Y with a negative in front. If you catch the object at the same level that you release it. Okay, so that is only true if you catch the object at the same level you release it. Now, so what if you what if you miss, right? What if you miss and you couldn't catch the object when it's coming down? Well, if you miss, well, then the object can go even faster vertically. Now remember, horizontally it's still only going to be that number at the beginning, and it's never going to change. Okay, so now to begin, let's put everything that we have said on record. So first of all, why does the object only accelerating downward? Well, because of our good friend, gravity, right? Gravity only goes this way. So gravity only goes in this direction. So we know that. So if gravity only goes in this direction, then obviously we're going to have an acceleration that is only in the y direction, which will only affect the y direction speed, right? The vertical speed. So it's only in the y direction. Now, okay, so now let's fill in some of these points that we mentioned. Now let's write down. An object launched into the air tends to follow a parabola. We call it a parabolic. So parabolic path. If you break down the velocity into x and y components, you will discover that both sides are perpendicular to each other. So the x and y components of the speed and are perpendicular to each other. So perpendicular, and therefore totally independent. So the x direction, all the numbers in there, is independent to the y directions. Okay, now this fact we have already mentioned. If you catch the object at the same height that is released, then its landing speed will be the same as its releasing speed, except the angle will be in the opposite direction. So it will be exactly the same speed, except that the angle is in the opposite direction. That means, for example, if you're launching something with a speed of, let's say, 10 meters per second with an angle of 50 degrees, now by the time the object reaches the other side, assuming that you're going to catch it on the level ground, so by the time the object reaches the other side right here, it's going to land on the ground with exactly the speed of 10 and exactly the angle, but negative 50 degrees. Well, not negative 50, but on the other side. Okay? So it will be the same number on the other side. Now, some of you in here might say, hey, Mr. Chang, don't you have to add a negative on that 10? No. You only do negative if the direction is directly south or directly west. Now, if you have an angle that's kind of like this way, then, well, just tell them an angle. If you have a vector that's going in like some weird direction, just tell people an angle and tell them like below horizontal, above horizontal, log of ease, something like that. You don't have to say like negative because, it's really hard to tell like, is that positive or negative, right? But if it's directly south then, or directly west, for example, then okay, that's negative. If it's directly south, then you say, okay, yeah, that's negative. But when you have something that goes like this and you're like, is that negative or positive? You usually don't say negative or positive with this. Now, if you break it into component, then you can say the components are negative. Otherwise, just give them an angle. Okay, so for the x component, all right, so for the x component, we have no net force after release. So yes, we are pushing the object at the beginning, but the moment that we are done pushing the object, it is not going to have any force going to the right or going to the left, right? So no net force in the x direction. And therefore, since no one is pushing, then the acceleration in the x direction, right? Acceleration in the x direction is always 0. So we don't have to worry about it. Now, when the acceleration is 0, we get constant speed though, right? So we get constant speed when the acceleration is 0. What is so cool about constant speed? Okay, if you look at your equation or your formula sheet, right? The big three. The big three leads acceleration to work. So if you don't have acceleration, okay, if you don't have acceleration, then you actually cannot use the big three. Okay, what were the equations that we used before using the big three? This one, the only equation that we actually begin with at the like velocity equal to distance over time. This equation is good when acceleration is 0. When there are acceleration, then you use the big three. So in the x direction, now this is the horizontal component, right? The one that's going, either east or west. So in the x direction, you only have one equation to use, this one, and no one else. So, for example, in this equation, what is your Vx and dx? Vx is simply your horizontal component of the velocity. So, for example, you have an object launching at an angle, and so, for example, and then you have like an angle in here of like 30 degree, 40 degree. Now, this Vx is this part only. Like this is called Vx. So this is your V initial, but I'm talking about the horizontal component of that only. Not the vertical, but just the horizontal part. Okay, so only the horizontal part. Now, then what is dx in this case? Well, dx is called the range. The range. Now, when an object is flying through the sky, right, like this, how far can it cover horizontally is called the range. Okay, so dx is the range. It's the distance that the object traveled horizontally. Okay, the range. Range. Okay, sometimes called the range. Now, so that means in this equation, it turns out that in order to find out how far can your object actually go, you just need the horizontal component of the velocity and give me the time, right? If you give me the time, then I can solve everything for you. Now, okay, that's good. Now let's look at the vertical part, which is the more difficult part. Now, this vertical part is basically our notes from 2 days ago, the free fall part, the free falling object part. That's exactly the same in here. So in the y component world, which is the component that goes like up and down, north, south, south, up and down, like up in the sky, down to the ground. There's always a constant acceleration from gravity, and it's always going to be negative 9.8 meter per second square if you are on Earth, if you are near the surface enough. Now, because you have acceleration, then please use the big three. So V final equal V initial plus AT. So you're only allowed to use the big three in the vertical world, not in the horizontal world. Now, also, there is one limitation. The numbers that you put in can only be the vertical version of that, not the horizontal version. Now, what's the difference? Again, right? So you're launching an object, you have some V initial, and we only care about the V initial Y component. Okay, so assuming that you have like an angle and everything. So it's only the Y component that we care about. So this is your V initial Y. So technically speaking, you can add a little Y to all of the measurement except for time. Time does not have direction. So time, you cannot say, accelerate, you cannot say time in the Y direction. There is no time in the Y direction. The time in any directions are the same. So your big three is now modified into this set of three. So when we say final velocity, we only mean the Y part. When we say initial velocity, we only mean the Y part. When we say acceleration, the gravity one, which is only Y. And that's everything. Now, we have two worlds, and these two worlds are parallel universes, right? So like in science fiction, you cannot allow anything to travel between these two worlds except for one superhero, which does not have direction. So it can travel through both worlds. And that is time. Time is a scalar quantity. Now remember what scalar quantities are. These are the quantity that does not have direction. Therefore, it can actually travel through both worlds. Time has no direction. So time, the same time that you see in this equation, in the Vx equation, is the time that you see in the y equation. So the times are the same. Now, other than that, distance are not the same, velocity are not the same, acceleration, one has it, the other one doesn't even have it, are not the same. Okay. So, level 1 of kinematic questions. Someone sits on the roof of a house, which is 12 meters high, launch a water balloon from a slingshot at 25 meters per second, and the slingshot is fired horizontally. Now, remember, this type of question, when I say level 1, means it's actually the easier type. So someone is sitting on top of a building, which is 12 meters, right here, and she's going to launch a water balloon. Now, but the initial launch of the water balloon is completely horizontal. Completely horizontal. So this initial speed is completely horizontal. So this V initial is 25 meters per second, but it's completely horizontal. Now, predict, right? Make a prediction first. Which way would the ball go? Well, I think most of you would agree with me that the ball should just be going like this way at the end, right? So the object, by the time it hits the ground, would be going like, somewhere like this, right? So, of course, it's going to have a speed that is, larger than 25, right? It's going to have a final speed or something that goes this way, right? Now, but we don't have to worry about that, not yet. Okay, so this is your V final, right? This is your V final. Okay. So V initial is 25. So there's V initial, 25. And then by the time it hit the ground, it's going to have a V final that goes like in weird direction. But be careful. What is the question asking? Number 1, how long will the object be airborne? Number 2, how far will it travel? Now the first one, how long will the object be airborne, is a time question. This is one of those airtime questions. So airtime question. Wait, we have done airtime questions before in Ph11. Airtime question is always calculated with those Ph11 equations. So you have V initial, V final, and then we get time, right? Yes, you remember it right. So time questions are always solved with the vertical component. Okay, so the vertical or the y direction. So if you want to solve for time, you're always going with the y direction. Okay, and now what is the next question asking? How far will it travel? How far will it travel is the range. How far will it travel is the range of the object. Now, which is the distance right here, right? This is the range. How far will it travel? Which is a horizontal direction that we need to worry about. This is the range. Now, remember what we said before, right? The horizontal speed affects this horizontal range. Wait a second. Look at your V initial. Isn't your V initial horizontal speed? Your V initial is only horizontal. Wait. I want horizontal distance and I have horizontal speed. Oh, let me go up. Let me go up to the equation. Oh yeah, I can find it if I have time. I can find this if I have time, right? So you look at that equation, it only has 3 things on it. Horizontal speed, which we have, that's our initial speed, is only horizontal, and it will remain exactly the same throughout the entire fall. So, for example, when it's in here, what would that speed look like? Well, when the object is in here, the speed is going to look something like this. But if you only look at the horizontal part, it is still 25. It will just have some like mysterious vertical part that we don't care about. Not yet, right? But if you look at the x part is always 25. Doesn't matter where you measure it. Remember, that is the observation that we have from our simulation. So your Vx is always 25. Even the moment before you just hit the ground and, break a hole in it, it's still just 25. So your Vy is, doing crazy things, but your Vx is 25, 25, 25, 25, 25 from the beginning to the end. So we don't have to worry about Vx. If you want to get that range, just get the time somehow. Okay, so here is our two things that we need to get. So how far will the object travel? Well, I have my Vx. Yes, I do. It's 25. I have to get a time. And once I have time and my Vx, I'll get the range. Okay, so now let's get the time. Okay, let's get the time. So the time is a Y business. Time is always a Y business. So we're going to the Y world. Okay, so we're going to the Y world. So what would the Y world be? Now, the Y world is a world where only the objects that is in Y direction, or only the quantity in Y direction, can actually exist. We are going to the vertical world, the Y world, right? Now remember, the vertical world will only have vertical numbers. Okay, so what are some vertical numbers? I know my acceleration. What is my acceleration vertically? It's gravity. So it's always negative 9.8 meters per second because gravity is only in the Y direction. So I have one thing. Do I have my distance or displacement? Well, in the vertical world, yes, we do have a displacement, and that is 12 meters. But we now have to ask the question, did we drop 12 meters or did we go up by 12 meters? Eventually, the ball dropped by 12 meters, right? It went down. So, negative 12 meters. You have to put that negative in there, otherwise the entire question will collapse. You must put that negative in the dropping distance. It's dropping. The question could be reversed. You're throwing a ball upward. Okay, that's different. But in this case, you're dropping 12 meters, so you lead that negative. Okay, what else do we have? Do we have V initial Y? Do we have V initial in the Y direction? This is a very tricky question. Do we have an initial speed in the Y direction? Now, you look at my initial speed. Our initial speed is 25, but that's only in the X direction. So what is your initial speed in the Y direction? What is your initial speed in the Y direction? Okay. So if our initial speed only has X direction, then that means the Y component is 0. Okay. The Y portion of your initial speed is 0. Now, because you have to look at it this way, there is nothing different between this object dropping like, going sideways and dropping like this, compared to just like a ball dropping like that. Okay? There is no difference between these two scenarios. As a matter of fact, your V initial in the Y direction, now this is all in the Y world, will be 0, and then it will be exactly the number that you have on the other side, your Vy, and then it will be exactly the same number that you have at the end. You know what? That's your little secret. Even the time will be exactly the same. Kicking a ball horizontally doesn't actually make it go down to the ground faster. It will be exactly the same speed and same time as if you just accidentally drop the ball. So for example, at the end, after we finish this question, we'll discover that it takes about 1.5 seconds to drop to the ground. And it will be 1.5 seconds this way or the questions. It's exactly the same. So dropping an object horizontally, kicking an object off horizontally takes the same amount of time to reach the ground compared to having the object just go straight down. The time is exactly the same. Okay, it's surprising, but that's actually how it works. It's exactly the same time and same speed. Now remember, gravity affects everything equally. So, and your horizontal numbers, motion, is independent to your vertical motion. So vertically, your initial speed is still nothing, even when you're kicking an object sideways. And vertically, your acceleration is negative 9.8, which is the same as, if you just drop an object. And vertically, that's how you get the time. So that's how you get the time in both situations. So now, if you believe in that, then V initial, when you have a horizontal object launch, right? When you have a horizontal object launch, V initial in the vertical world is 0. Now, and then you can use this to get time very easily, right? You can use it to get time very easily. So we need big 3 because we have acceleration. So we need big 3. So one of the big 3 is going to help us with that. We don't have V final Y. I mean, yes, we could find it, but why do one more calculation, right? So we don't need it. So which one has no V final? Oh, the one with the displacement. There. V initial t plus 1/2 at squared. Now remember, everything in here is the one in the y or the vertical world. Okay, but your V initial y is 0. Oh, that's why we picked this equation. That will kill off this entire term. Fun. So you only have this and the 1/2 and the acceleration and the t squared, and you're only looking for, well, that t squared. You have all the other numbers. For example, displacement is -12. So we put -12 in there. And then we have 1/2. And then we have acceleration, which is -9.8. So we put that in here. And we're looking for the time square. Okay, so time, and then we will square it, right? So first thing to do, again, so today I'll go through the calculations a bit right here. So t squared. Now at the end, we're still wanting to find that t squared. You see double negative at this moment. So the double negative sign can cancel out. So you don't have to worry about the negative sign. Now, both in the calculator, 12 divided by 4.9, and then a square root later. The final time is 1.56 seconds, about 1.5 seconds approximately, right? Okay, so it will take 1.5 seconds for the ball to hit the ground. And it doesn't matter if you're kicking it horizontally or if you're just dropping the ball. It will take 1.56 seconds for an object to drop 12 meters. No matter if you're doing it horizontally or just dropping the ball from your hand. Okay, so now we answer the first question. Oh, we have time now. Nice. We have time. We can do range. Okay, let's go back. Look up at the equation. The range equation requires two things. Vx and time. And at this moment, we have both of them. Vx is your initial speed, and time is what we just calculate. Okay, super easy then for the range. So now we get the range. Okay, so now we get the range, which is an easy thing. So B, what is your range? Horizontal distance, dx. Now we're in the x world. Okay, x world. So the horizontal world. Now in the horizontal world, only one equation survives. This one. Okay, in the horizontal world, only one equation survives. And we have both of the numbers. For example, horizontal speed is 25 from the beginning to the end meter per second. And the displacement is what we want to find, whereas time is 1.56 seconds. That is from our last calculation. You will multiply both sides by 1.56 to get rid of that division. And once you're done, you get a range of about 39 meters. Okay, so what does that range actually represent? Of course, it's just the landing distance, right? So your object is launched horizontally. It takes about 1.5 seconds-ish, 1.6 seconds to hit the ground. And during that 1.6 seconds, your object land somewhere 39 meters from the beginning point. Level one is done, right? So level 2 projectile, level 2. Okay, so level 2, now remember, level 2 is this situation right here. So you're launching on a level ground like this, right? Okay, so you're launching at a level ground like this at an angle, to the sky. Now, in our question, what is the launching speed? The launching speed is 22 meters per second. Actually, let's do exactly that. 22 meters per second. What is the launching angle? 35 degrees according to our questions, right? Now, that's exactly this. Okay, that's exactly this situation. Now, and then we're going to launch the object. Okay, now we might have to zoom out a little bit. Okay, there we go. All right, right here. So we are landing somewhere 46.4 meters after the initial launch. So this is a situation we are going to analyze. Okay, see that again. So, and then you catch it at the same height. Okay, so initial speed and then catching the same height. So this is level 2. Okay, this is level 2. Now, okay, so right here. So what are they asking us to do? How far downfield is the receiver? Okay, so apparently in this question is a quarterback throwing a football to the receiver who is on the other end trying to catch the ball. Launching speed is 22 meters per second. Launching angle is 35. But according to our simulation, we already know the answer to this question. It's going to be 46.4, right? Yeah, okay, so how do we get 46.4? That's the answer. By the way, that's the answer. So how do we get it? How do we get it, right? Okay, so how far downfield is the receiver? How high does the ball go? Which is this height right here. So I can actually take this right here. The height is about 8 meters, right? 8.1 meters at the maximum. Good. And then what else are the action? What was the question asking? What other angle could the quarterback throw the ball to reach the same displacement? Oh, okay. Now this is a funny, not a funny question, but you know, it's a interesting question to think about though. So you know, sometimes now you want your receiver in here, right? So receiver is at the target location right here. So you're launching this object at a 35-degree angle. But what if there's a wall? What if there's like a physical wall that is too tall in front of you and you cannot throw it at this angle? Is there any other angle that you can throw to get to the same distance so that the receiver can catch the ball, but you can avoid that wall? So what if there's like a giant wall in front of you and you know you cannot just launch it in 35 degree, you will just hit the giant wall. So what do you do? Okay, so those are the 3 questions. Let's answer them one at a time. Okay, so now the first one is 36 meters 46 meters downstream. So how do we get that? Now, okay, so to begin with, let's draw a football. Okay, so we have to start by drawing a football right here on the field. Okay, so let's start by doing that. Okay, so have a diagram first. Okay, so here's my football, right? And now as my football is going to go like initially, it's going to go at 22 meters per second. Okay, so initially it's going to at 22 meters per second. Now I might, okay, so and then we have to break it into component. So at the beginning, that is 22 meters per second. So 22 meters per second, that's my V initial. And then at a 35 degree to the horizontal angle. Okay. And then predict what we'll do, what happens is going to be like this. So I predict that it's going to go up and like this, and then it's going to the highest point, and then it's going to hit the ground, and then it is going to be right here. So by the time it hit the ground, it's going to be all the way on the other side. So like this, that's the highest point. And by the time it hit the ground, it's going to be somewhere here. And it's going to hit the ground like this. Now, but remember, we are catching the object at the same location that we release it. Therefore, I mean, not the same location, same height. Therefore, the speed will exactly be the same, 22 meters per second. Now, what is the only thing that's different? Well, the angle will be going to the other side, which is 35 degree below ground, below horizontal, instead of above ground, above horizontal. All right. Okay. So that's the situation. Now, what else can we tell about this? Well, number one, let's break it into components. Now, this is all I want you to learn from last day's lesson. Breaking things into components. Now I'm going to do a, what color do I use? I'm going to do a orange component for vertical. Okay, so vertical component is orange for me. And the horizontal component is going to be green for me. Okay, so orange and green. I want to pick 2 colors that stands out. Okay, so orange and green. Okay, green is here. Orange is there. The green is the VX. The orange is the VY initial. Okay, so V initial Y. All right, now, how fast can you get me those 2 things from last day's work? Which one takes the sine and which one takes the cosine, right? Okay, so number 1, let's do the V initial Y. V initial Y is equal to V initial, which is 22, multiplied by either sine or cosine of that angle. Now, is it sine or cosine? Well, look at this triangle. you have this angle, that's the hypotenuse. This is the opposite, that's the adjacent. Now remember, opposite is with sine, right? So this side takes the sine ratio, and this side takes the cosine ratio, always. So for my vertical, I'll take the sine ratio of 35 degrees, and then throw it in a calculator, you are done. Next, well, might as well get the horizontal one, right? Vx. Vx is going to be 22, which is your V initial, your hypotenuse, multiplied by the other one. If you can pick one, then the other one is free. It's always just the other one. If the first one is sine, the other one is cosine. Always works. There we go. Now, the third thing we have to note, an extra thing that we have to worry about is direction of those components. You look at the y direction, it goes up, north, north, up, it goes up. So up, positive, good, leave it as positive. Look at the x direction, goes this way, which is right hand side is positive. Okay, so leave them. Positive is fine. Now, take a calculator and just run it really quickly. And we get, I'll even give you the number. I mean, running this is a simple thing. So for example, Vx is going to be 18, Vy is 12.6 initially. Okay, so it has to be that quick. All right, now you look at those two numbers and you go, okay, now Vx is going to stay 18 forever, right? Vx is going to stay 18 forever. For example, when the object is at the highest point up in the sky with your, maximum height location, Vx is still 18. It's never not going to be 18. Even the moment you hit the ground, Vx is 18. Vx is always 18. I mean, the moment that you get it once, it's the same number over and over again. Vx will only be 18 and nothing else. Okay, your y speed, okay, fine. Your y speed might be different. So for example, in this case, your initial y speed, right? Initial y speed is 12.6 meter per second. Aha. But what is your final y speed? So we go to the other side. Your at the end y speed, right there. At the end, your speed goes downward, right? So at the end, your Vy goes down. So we can even call it V final y if you want. And that is going to be exactly the same as your V initial. Except, so 12.6, except negative. So it's negative 12.6 meter per second. So other than that, it's exactly the same. Okay, so the first question, or question A, is asking us for the range. Okay, so how far downfield is the receiver, which is asking us for dx. But remember, we did the last question, and we know the procedure of getting this. In the last question that we did, remember we actually had to get time first before we can get this dx, because yes, we have Vx. Yes, it will be easy to get distance x, but we need time though. And time is the time, you can only get time from the vertical side. So, okay. So that means, even though the question is asking us for the range, however, we cannot do range. Not right away. In order to get range, we have to get time first. Okay, you have to get airtime first. Now, and getting airtime means we are going to the y, the vertical world. So let's go to the vertical world, y direction. Okay, let's go to the vertical world. Now, in the vertical world, let's write down everything. V initial vertically is 12.6. Now remember, don't write down V initial. V initial is 22, which is a number that you're no longer allowed to use or even look at. Remember, most common mistake that I see when people do this kind of question is going back to use that old number. The number 22, right? Remember, the initial value that the question gives you is useful for about 5 seconds in your calculation. It's useful for getting v initial x and vy. That's it. That 22 cannot be used ever again in this entire question. If you find yourself plugging in that 22 in anything in the question, other than the first 5 minutes of getting v initial x and v initial y, then the question is wrong. Whatever you're doing, if you use 72 again, it's automatically wrong. So once you get your vx and vy, I want you to go to the question and just scribble it out, so you'll never see it again. That number is there to trick you into using it. You should never, never, never touch that number ever again after you get yourself your vx and your vy initial. That's it. That number is no longer useful. It's there, well, basically, to hurt you more than it helps. For example, when I write down my v initial, I'm not writing down 22. It's 12.6. It's the vertical v initial. And then acceleration. Acceleration is easy though. You have gravity, right? Negative 9.8 meter per second square. And then you have, or time is what we want to find. So that's okay. So we don't know the time. It's fine. We are looking for the time. So it's okay. We final y. Oh, yeah. Because we are catching the object at the same height. So what goes up must come down with the same speed. Just put a negative in front. Right? What goes up must come down with the same speed with a negative in front. Okay, cool. Put the negative in front. Put the negative in front. There we go. Put the negative in front. All right, so it's 12.6 but negative in front. There we go. We can get time from this. Super easy. All right, so I guess in this equation we don't have displacement. So we are going to use the equation with no displacement. V final equal v initial plus at. Now this one doesn't have displacement. And we just have to make sure that we are getting time. So v final is negative 12.6. V initial is 12.6. Acceleration is negative 9.8. And time is the unknown. Now I do have to warn you though, there are a lot of negative going on in here. And what is the first item to go? The 9.8 or the 12.6? Who is the first one to go? Has to be the 12.6. And do not combine it with the 9.8. Subtract it on the other side. Subtract. So you're going to have like negative 2 minus 2, which is just double the negative, right? Become negative 4, for example. So negative 12.6 minus 12.6 is going to be double of that, which is 25.2, I believe. Now, if my math is going funny, please help me out and tell me that. And then we have negative 9.8. And the time is what we want. So now divide both sides by negative 9.8, drop the negative sign, and we are done. Time is done. The only passenger that can travel between the two parallel universes of vertical and horizontal is now within our control. Okay, so this time it's going to save us. Once we have this time, getting range is super simple. Now we can get the range. Now we move back. We're going to travel to the other universe. We're going to travel to the X world, right? The horizontal world. So in the X world, only one equation is allowed. And it will be the same one like the last question. So we need Vx and dx. Dx, so it's the range that we want to get. What is Vx? If you forgot, I think I remember, it's 18. Yep. Initial, the horizontal speed is 18 from the beginning to the end. So 18, just 18. So by breaking here, so initial speed is 18 meter per second, 18 meter per second. And then displacement, dx, and then time, right? Time. So time is 2.57 seconds. So now multiply both sides by 2.57, multiply, right? And then you get your range, which, according to our simulation, how much? 46.4. Let's try. Multiply those two. You will get 46.4. Ooh. There we go. So this is the first thing that they're asking for. Now, so the legs part, okay, so this one is done. So how high does the ball go? Okay, so that's maximum height. Now, what is so special about maximum height? So maximum height, remember, has a vertical speed of what? What is the vertical speed at the maximum height? 0. At the maximum height, your vertical will have no speed. It only has a horizontal speed. And that will help us get this maximum height right here. So this is called the maximum height, right? So we will have to use the maximum height speed and the maximum distance, and then that will be something that we can do. So let's take those values and transfer it down here, some open space, and let's get that there. So I want max height. That means it's a dy, maximum dy, and so v initial y. So we're in the y world, right? Still 12.6 meter per second. Acceleration is from gravity, negative 9.8 meter per second square. At the maximum height, we have a vy that is equal to 0. Now, this is only true when you're at maximum. So when you're at the maximum height, your vertical speed is momentarily 0. What are we looking for? dy. Oh, it seems like we have 3 things out of 4. So there must be an equation that can help us do this, right? So let me think. With no time, wait a second, Mr. Chang, we have time. Why are we not using time? I thought we have time over here. What on earth? What is that thing for if we're not using it? Well, be careful. Be careful though. This time that we just got is the time for this entire trip. But the maximum height is only from here to here. The maximum height does not take the entire 2.5 seconds to reach. Actually, to be honest with you, it takes exactly half the time to reach that. So 1.28 seconds approximately. But it's okay. If we don't use, even if you don't use half the time, we can still get it though. So look at this equation. It's not that difficult to get dy. So the one with no time is this one, right? V final square, V initial square, plus 2ad. So this one has no time in it, which is perfect. We don't have to do an extra calculation for the time. And you just, okay, so V final is 0. Convenient. V initial is 12.6. Okay, but we're going to square it. Fine. 12.6, but make sure squaring it. Okay, squaring it. Plus 2 times the acceleration, which is negative 9.8, multiplied by displacement, which is d. Now, so this is what we're looking for, that d right here. Okay, so first thing, get the square done, move it over, and you get negative 159 approximately. Okay, now let's combine these two terms so that you can write it right here. 2 and 9.8 is 19.6. And yes, there is a negative in front. This negative right here is still here. And now the displacement, which is right there. Okay, so you got all of those. Okay, final step, drop the negative, right? Double negative, you can drop it. Divide both sides by 19.6. Your maximum height. Your maximum height. dy, I guess I should say maximum dy is 8.1 meter approximately. Okay, now approximately 8.1 meter is the maximum height that you can reach. Which then we go back to the simulation. Remember, we we took the measurement right here at around the maximum height. Yeah, 8.11 meters. See that? 8.11 meters. Yeah, pretty close. 8.1 meter, 8.11 meter at the maximum height. That's good. That's pretty close. All right. the final question then is at what angle can we launch this ball so that the receiver can still catch it if we have like a giant wall in the middle? So that we're going to run it with our simulation, which is over here, and 35 degree, right? 35 degree can get us to that location. So that's what we want. Now, at what other angle can we get to that location? Let's try 45. Does 45 works? It's too far. Okay. So how about 55? How about 60? 60. How about 60? Will 60 work? Will 60 land on the same target? Now remember, if we land here, then we so close, so close. Okay. How about what else? How about 55? I'm just randomly picking things. I'm randomly picking things. Hey! Oh, 55 works. So 35 and 55 degree. So, 35. Okay. Let me do it again. 35 is the original launching angle. So the question was, what other angle can we launch? And we find out that 55 will actually get you the same location, except it will stay in the air for a bit longer. But the right receiver will still be able to catch the ball because it will land in the same location, right? Okay. So I guess the answer is 55 degree. So other angles, right? So I guess, okay, so our initial angle is 35 degree. And I guess another angle that will get us to the same height is 55 degree. So that's my answer. But we use a simulators to get the answer though. I mean, on the test, we're not going to have a simulator. So what is, so we have to find, we must be able to find a collection between these two numbers. Is it off by 20 degree? Or maybe that's a collection. Maybe it's off by 20 degree. And that's how you can get it. Okay, well, let's try one. Let's try one more. Now, this time we're going to pick another angle. Let's pick an angle that is, maybe we pick what? Like 30. Let's pick 30, right? So let's launch the 30 degree object and see where it lands. Now it lands somewhere here at about right here, 22.7. Okay, so at 30 degree, it goes to 22.7. Now let's see what angle should we pick. How about 40? Will 40 get there? Oh, no. 40 is nowhere near. How about 50? Now 50 is 20 degree from 30, right? So that's exactly the same difference as our last pair. Oh, no. That's not even close. That's not even close. How about 55? Bing. It's getting closer. How about 60? Come on. You can do it. You can do it. Oh. 60. Okay. 60 did it. So, anyways, 60 and 30 land on the same location. Let me double check. 60 and 30 land on the same location. Let's write that. If the first one is 30, then to land on the same location, it is 60. Damn, it's not 20 degree different. What are the patterns? Can someone venture a guess? Right? Now, I want you to do this in your head. Add them. What is 35 plus 55? What is 35 plus 55 degree? What are they equal to? 90. Thank you. Okay, so now I want you to do this one. What is 30 plus 60 degree? 90. So that is the pattern. They have to add up to 90. So now here is the, question. What if you launch something at 15 degree and at what other angle will you be able to catch it? At what other angle can you launch it so that you're catching it? 75 degree. Because at the end, the two numbers has to add up to 90 degree. Oh, that's the pattern. Okay, so now you know how to predict that. Okay, so whatever launching angle you have, 90 degree from that is another launching angle that you can get to the same location and, with a bit longer of the time. The bigger the angle is, the more time you actually have to stay in the air. Usually that's the case. But you will get to the same location if that's what you want. That's good.